talk about water molecules and special properties of water. Water is a very unique molecule. It has a very specific shape. It has very special properties. Water is going to be one oxygen atom and two hydrogen atoms that are put on top. It's always going to have this Mickey Mouse ear kind of effect. It's going to be kind of bent with the hydrogen molecules, so water always looks like that due to some of its properties. Water's formula is H2O. My subscript here is showing 2, so that means I have 2 hydrogens, 1, 2, and 1 oxygen. Water is a covalent bond, so that means it shares electrons. It goes back and forth. Electrons can share between 2 to 6 electrons in a covalent bond, and they want to go with what's called the octet rule. So the octet rule is the rule of 8. Here I have hydrogen. Hydrogen has 1 electron each. When I look on the periodic table, hydrogen has an atomic number of 1. So that means it has 1 proton and 1 electron. I have oxygen. Oxygen has an atomic number of 8, but it has 6 valence electrons. 1, 2, 3, 4, 5, 6. This is what we look at when we're looking at bonds, are the valence electrons, and we want those valence electrons to have the rule of 8. The exception is hydrogen. Hydrogen wants to be like helium, so it wants to have 1 more in that ring. If we remember our Bohr models, first ring holds 2, second ring holds 8. We're kind of following that rule. So hydrogen wants to bond with oxygen, and oxygen wants to borrow these electrons too. So if I can borrow these 2 hydrogens, oxygen will have 8. Oxygen will pass one of these electrons to hydrogen, and then this one will have 2 for a little bit, this one will have 2 for a little bit. So all 3 atoms will be happy, and they'll both be stable because they'll be able to fit that octet or that full shell rule. Here's an electronegativity chart. When we talk about covalent bonds, we talk about 2 types. We talk about polar covalent and non-polar covalent bonds. Polar covalents are going to share electrons unevenly. Non-polar are going to share evenly. When we talk about water, water is polar, and this is why. I look at this electronegativity chart, and this is telling me how electronegative an atom is. And when you hear the word electronegativity, you need to think greediness. How greedy are these atoms for electrons? The ones that have a high electronegativity are super greedy. They want all the electrons, and they really don't want to share. The ones that are lower, over here with my alkali group, these are they really could care less. If they have electrons, they're going to come in for a little bit, but then they're more than happy to share them out. I look at oxygen. Oxygen's electronegativity is 3.5. Hydrogen's is 2.1. This has a higher electronegativity than hydrogen, so this is going to be very greedy for electrons. It's going to want to hold all those electrons. It is going to just pass it to hydrogen every once in a while and come back. So the example I use is a kid who has their favorite toy. Are they going to want you playing with their favorite toy? No. And when they're forced to, they're going to give the toy away just for a little bit, but they're going to pull it right back. And that's kind of how oxygen is. Very greedy and wants to keep all the electrons for himself. Water has a covalent bond, so that means oxygen's highly electronegative, greedy for electrons, and this symbol here is showing electronegativity. When I look at my water molecule, I see that oxygen is going to hold more electrons most of the time. Since it's going to have more electrons, it's going to have an overall negative charge. Remember, I only had 6 valence electrons. I have an atomic number of 8, so a neutral oxygen atom is also going to have 8 electrons. 2 in that second ring, 2 in that first ring, 6 in the second ring for a total of 8. But now I've brought in 2 more electrons. So now oxygen no longer has 8, it now has 10. 2 in the first ring, 6 in the second, plus 2 more. So now I have 10. So I'm going to have more electrons than protons, so I'm going to have more of a negative charge. Hydrogen has 1 proton and 1 electron. Hydrogen has donated its electron to oxygen. So hydrogen now just has a proton. There's no electrons. So hydrogen just has a positive charge. This hydrogen's going to do the same thing, and that one's also going to have a positive charge. So now what happens is there's going to be times where, remember, oxygen doesn't want to give away those electrons, but it's going to be kind of forced to. Oxygen will donate one of its electrons to hydrogen just for a second. And hydrogen will now have a slight negative charge. Since I have one hydrogen proton, I usually have one electron, but now I've gained an extra electron, I'm going to have more of a negative charge on this end just for a little bit. And then during that time, oxygen's going to have a positive charge. These poles are going to flip. So I'm going to have a positive, negative, but then remember, oxygen wants all those electrons back. And when it does, now oxygen's going to be more negative, hydrogen's going to go back to being positive, and those poles will keep flipping and going back and forth. That opposite attraction is kind of what allows them to stay together. Magnets, think of magnets. Magnets attract. So since oxygen's extremely greedy for those electrons, they're going to spend most of their time here around oxygen. The electrons are unevenly shared. Oxygen's going to have these electrons most of the time. So when they're unevenly shared, they're going to be polar. And you can look at an electronegativity chart. If my charges are way off, if they're not very close at all, you can pretty much guarantee that it's going to be some type of polar molecule. The closer they are in charges, those would be a nonpolar. They're going to share evenly. Oxygen can be nonpolar if it shares with itself. Oxygen with another oxygen, those will be nonpolar. They're the same charge, so they're going to switch back and forth and go back evenly, and one's not going to have one longer than the other. When the charges are different is when I'm going to have that polar pool. Here I have fluorine. Fluorine is going to have the same charge. Remember on my electronegative table, fluorine, really, that's the most electronegative atom that's on that chart. Fluorine is going to be nonpolar because it's sharing with itself. This charge is the same charge as this, so one is not going to pull more than the other. So these electrons are just going to swim back and forth evenly. One will not spend more time with the other. Here I have hydrogen and oxygen. Now remember, this is going to make water. My molecule is bent. Oxygen's going to have such a pull, it's going to pull the hydrogens here. These hydrogens are going to try to pull away from each other because they're positive. Remember, likes repel, but it can't. The hydrogen's going to keep pulling it. So my electrons are being passed back and forth. They're going to spend most of their time here. Every once in a while it comes here, and every once in a while here, but it's going to spend most of your time with around the oxygen. And that's why water's polar. Here are some examples of polar and nonpolar. We've talked about water, negative, positive, but when I look at my electronegative chart, carbon and hydrogen are very similar in charge. So these are nonpolar. Here I'm going to have them, they're just going to keep evenly just distributing electrons back and forth. One will not have them longer than the other. Oxygen, really electronegative, but so is the other oxygen, same charge. So those will go back together and those will share evenly back and forth. Water can create what are called hydrogen bonds. And what happens here is oxygen, so greedy, is not even happy with the 8 that it has now. It has a full shell. It shouldn't want any more. But it is so greedy, it wants more. So it's trying to pull the electrons off these other water molecules, but it can't. It already has a full shell. But this is similar to a magnet. This negative charge is pulling some of these positive hydrogens towards it. And this is the thing you need to get with hydrogen bonds. Nothing passes. You have a passing of electrons through a covalent bond. These are those solid lines. So I will always have electrons passing through covalence. Hydrogen bonds don't pass anything. Think of them like a magnet. It's going to be attracted to that. What's nice about hydrogen bonds is they break apart and come together very quickly, very easily. So if I have water, liquid water, you put it in a bowl and you know how it rolls, and you can go down windshields and these beads will come together and then they can break apart. Those are hydrogen bonds just kind of forming and breaking all the time. If I have a solid piece of ice, that ice, those hydrogen bonds are more fixed. I just can't take a piece of ice and twist it and break it apart. I can't do that. And with gas, steam, the bonds are so far apart they're not even touching until they start to coalesce and come back together and condense as water, liquid water. So one water molecule can have 4 hydrogen bonds. So let's look at this water molecule here. This hydrogen is going to be attracted to an oxygen water molecule in another spot. This hydrogen will be attracted to another water molecule in another spot. This oxygen atom is going to pull 2 hydrogens towards it. So see these dotted lines? These dotted lines represent a type of hydrogen bond. Usually there is some type of dashed line. So these are going to show hydrogen bonds. So again, think of them as magnets. Nothing's being passed back and forth. But one water molecule can have 4 hydrogen bonds. These break apart very easy. They come back together very easy. We talk a lot about hydrogen bonds when we start talking about DNA. When we have matter that needs to move or fix itself fast, it's usually some type of hydrogen bond. Here I have a bunch of water molecules together, and if I poured water on a table, I could take my finger and I could run through the water. And when I run through the water, I can push those water molecules apart, and then as soon as my finger comes past it, it will push it back together. So I could run my finger through these bonds and break them, and then the magnets will just kind of pop, pop, they'll all come back together again. So hydrogen bonds, they're really useful. They're very weak, but they're extremely useful. So let's talk about properties of water. Water has some very specific characteristics. One is cohesion. Cohesion is the attraction of molecules to the same substance. So water can attract water. Again, the hydrogen bonds, they're going to pull them together. So water can attract to itself. And we've seen this like I was mentioning with the windshield. Water droplets will condense, they'll come together, they'll coalesce, and I will have these droplets. They can get bigger, they can break apart and get smaller. So all of these hydrogen bonds are holding and pulling all of these other molecules together, nice and tightly packed. It also causes surface tension. So if you've ever seen something floating on water, you have water bugs that will go, the hydrogen bonds are together, the weight of the foot of that insect or the leaf isn't enough to break that surface tension. Those hydrogen bonds are staying tight together, allowing those water molecules to stay together and not fall apart. Now, if I break surface tension, you're pulling apart those hydrogen bonds. If I have a penny, and some people will do like a penny lab where you see how many drops you can put on a penny, you will see this pretty little bubble that will start to form. And all those are hydrogen bonds pulling tightly to each other. They don't want to let go till the force becomes greater than the hydrogen bonds, and it will break the bonds. You have adhesion, and this is when water attaches to other objects. Here I have cohesion, water to water, but this is adhesion, a water molecule to something else. With plants, they use the xylem and the phloem are kind of, you can think of them like blood vessels in a body. They're like the blood vessels for a tree. They allow stuff to move way up and come back down, and it's this constant moving. The way a huge tree like a sequoia or a redwood, they have to get water up to the very, very top. Water will attach to the phloem and xylem, and it will pull it up almost like a straw to the very, very top. And then that's how water will be able to move up in a capillary action or due to adhesion and cohesion. So capillary action is going to describe how water moves up a narrow tube or a paper. If you've ever spilt water and you had paper sitting next by and it was just barely touching it, you come back later, the whole paper's wet, or the paper towel or the clothes, it's capillary action. The water is getting pulled up by the fibers in the paper and the clothes, and that is pulling the water in. So this is caused by both adhesion, it's water attaching to the object, and cohesion, water attaching to itself. If you've ever seen a straw or like a graduated cylinder, you have a meniscus and a meniscus is formed by that too. Capillary action is going to pull it up the tube. Adhesion is going to make it attached to the side of the tube, and then cohesion are going to be the water pieces holding itself together. Water also has a high heat capacity. The amount of energy needed to raise the temperature of water and to lower water is pretty big. If you put a pot of water on a stove and turn on the heat, it doesn't automatically boil. It takes a little bit of time. And same thing when I take it off the heat, it takes a little bit of time for it to be able to cool down. So it has what we call a high heat capacity. It's able to hold water and release water slowly. Here I have an example. I have a pond, I have a lake, and I have an ocean. The sun is going to heat up the pond faster than a lake and then an ocean. This is also going to cool down faster than a lake and an ocean. A lake is going to take a little bit of time to heat up. So if you go on a really hot day, end of May, and you get in a lake, it could be really, really cold. It hasn't had enough time to absorb a lot of heat energy. But when you go in September, it's had all summer to absorb a lot of heat. The water is going to be a lot warmer than it was in April and in May. Same thing with an ocean. Oceans can absorb a lot of heat, but it releases the heat very slowly too. So it takes a lot to heat it up. It takes a lot to cool it down. This is why a lot of places that are by the ocean stay at a more maritime temperature, at a more constant temperature because of the water. Living things are around 60% water. So we use water to create chemical reactions in our body. If you become dehydrated, you don't feel good, water is really good at breaking down and starting chemical reactions and processes inside your body. Without these, we wouldn't be able to do a lot of these reactions. All right, that is it for today. It's a pretty short one, properties of water. If you guys have any questions, let me know. Talk to you guys later.